Welcome to a video about modern physics research, where today we are delving into string theory. Now, before getting into recent discoveries, I believe a brief history lesson is in need. In 1867, Lord Kelvin published an article on vortex atoms, in which he proposed that atoms consisted of vortex rings in the ether of space. Such vortex rings could be linked together to form complex structures. Atoms were known to exist because of the constant proportions demonstrated in chemical reactions. However, this article was from a time before the existence of electrons was known. Experiments by J.J. Thomson in 1897 led to the discovery of the electron as a fundamental building block of matter. In 1919, Theodore Kaluza formulated a theory based upon the general theory of relativity, but involving 4 spatial dimensions rather than 3. From his theory, Kaluza got electromagnetism as an implication. This held out the possibility of uniting gravity and electromagnetism. Albert Einstein liked Kaluza's work and supported its publication. Think of the start of string theory as a multi-generational cake recipe that has received mixed reviews from the public. That is until celebrity chef Albert Einstein receives a taste of your cake and approves of it. In 1968, Gabriele Veneziano used data collected from various particle accelerators to formulate the foundations of string theory. He constructed the dual resonance model after realizing he could use the 200-year-old Euler beta function formula to explain the physical characteristics of strongly interacting particles. In 1970, the name string theory is coined when 3 physicists, Leonard Susskind, Holger Nielsen, and Yoichiro Nambu, who used Veneziano's model to suggest that the universe is made up of tiny vibrating strings. I know you're here for a history lesson, and there's a lot more history regarding string theory, but these events are what basically started this whole string theory revolution. A bit more info on these scientists will be present in the description. Just know that the 5 central ideas of string theory come from more brilliant physicists and mathematicians. Now, moving on. What even is string theory? String theory posits that the most basic building blocks of nature are not particles, but rather one-dimensional vibrating strings that move at different frequencies, and determining the type of particles that emerges, akin to how vibrations of string instruments produce an array of musical notes, like a guitar strings vibrating to make sound. What is important to know about delving into the study? Well, that is the 5 central ideas of string theory. Comprehending the ins and outs of string theory requires extensive study, so here is a basic understanding of its core concepts. Number 1. Strings and branes. Strings are one-dimensional filaments that come in 2 forms, open strings and closed strings. An open string has ends that don't connect, while a closed string forms a closed loop. Branes are sheet-like objects that strings can attach to at either ends. Branes are capable of moving through space-time according to the rules of quantum mechanics. Number 2. Additional spatial dimensions. Physicists accept that our universe contains 3 spatial dimensions, but string theorists argue for a model that describes extra dimensions of space. In string theory, at least 6 additional dimensions go undetected, because they are tightly compactified into a complex folded shape called a Calabi-Yau manifold. Number 3. Quantum gravity. String theory is the theory of quantum gravity because it attempts to merge quantum physics with the theory of general relativity. Quantum physics studies the smallest objects in the universe, like atoms and subatomic particles, while general relativity typically focuses on larger scale objects in the universe. Number 4. Supersymmetry, also known as superstring theory. Supersymmetry describes the relationship between 2 types of particles, bosons and fermions. In supersymmetry string theory, a boson or force particle always has a counterpart, fermion or matter particle, and vice versa. The concept of supersymmetry is still theoretical, as scientists have not seen any of these particles. Some physicists speculate that this is because it would take incredibly high energy levels to generate bosons and fermions. These particles may have existed in an early universe before the Big Bang, but then were broken down into lower energy particles seen today. Number 5. Unified forces. String theorists believe they can use interacting strings to explain how the 4 fundamental forces of nature, the force of gravity, electromagnetic force, strong nuclear force, and weak nuclear force, create a unified theory of everything. This research is led by Clifford Chung, Aaron Hillman, and Grant N. Remond. In their work, they posed the following question: what is the math question to which string theory is the only answer? This approach to understanding physics is known as the bootstrap. A bootstrap calculation is a statistical procedure that uses random sampling to estimate the properties of a population. Think of it as you gathering a random group of 100 cats and asking them if they like hamburgers. 60 of them say they do, so you can now say that 60% of all cats like hamburgers. In the Physical Review Letters paper, the researchers discovered a way to bootstrap these string amplitudes, specifically constructing them through the creation of mathematical formulas. By implementing special mathematical conditions on their formulas for scattering amplitudes, which describe how particles interact and ultimately form, the group found that the amplitudes of string theory emerged as the only consistent answer. Assumptions were made for these equations, which aren't too important to understand the implications and applications that they do propose, but here they are. This is the bootstrap problem used. Further equations that were already established were used and able to be proven using these bootstrap assumptions. Hey, string theory is pretty cool. I know, right? The applications are pretty intriguing. Is that a string monster behind you? Oh no. Another possible direction for future work is the generalization to higher point scattering. This is in reference to the amplitude equation, the Veneziano amplitude. Since the Veneziano amplitude is a known solution of these non-linear equations in the space of sequence variables, linear permutations can be considered about it. As now that these mathematical conditions are known, it brings us a step closer to understanding if and why string theory must describe our universe. This breakthrough may be useful in better understanding quantum gravity. It seeks to reconcile Einstein's theory of relativity, which explains large-scale gravity, with quantum mechanics, which describes particle activity at the smallest scales. The development of tools outlined in the research can be used to investigate deformations of string theory, allowing the mapping of a space of possibilities for quantum gravity. The setup doesn't account for the effects or impact of gravity, so that is a case for a future study to perhaps follow up upon. But hey, that's just the theory, a string theory. Thanks for watching.